right, this will be AP Chemistry Notes, pages 29 and 30. And we start with just a classic thermochemistry type of question here at the top. This gives us a certain amount of a chemical. So 1 gram of methane. It's burned in oxygen, which is usual, and it produces this much energy. Now, when you see produces this much energy, please keep in mind another way of saying producing would be just to say negative 55.45 kilojoules. So producing or exothermic or negative is all saying the same thing. On the opposite end, we have endothermic or consuming or positive. And so be very careful this entire unit. Constantly be asking yourself, is energy going into the discussion or out of what we're talking about? You also have to be careful. And I like to give this example. Let's say I have my hand. And in my hand, I have an ice cube melting. And as the ice cube melts, I ask, is this an endo or exothermic process? Well, that's a pretty bad question because the answer is both. It would be endo to the ice cube, and it would be exothermic to my hand. And so if you're ever asked a question like this, or you need to figure out the direction, and the problem's vague, if the author's available, then ask the author. So like if it's a test, ask me, what do I mean? I'll try to be clear so that that doesn't happen. If you don't have the author available, what you do is you remove yourself. You have to be non-egocentric. So if we take this same example, what we would do is we'd say, let's not focus on our hand, let's focus on the ice cube. So we would say, without having any other information, if you had to choose, we would say that this is endo, because we're not so concerned about what's going on with our hand or the environment. It's what's going on with the item of discussion, which here is the ice cube. Or if you had a chemical in a beaker, it would be the stuff in the beaker, not your hand holding the beaker or the environment around the beaker. So I think a lot of people get things backwards because of that. All right, so it says ultimately we want to write a thermochemical equation. So it sounds really fancy, thermochemical. All it means is just include the heat. So I start by writing my reaction, CH4, O2, forming carbon dioxide and water, which is pretty typical combustion. And then you can write the energy over here to the side, which is my preferred way, or you can write it in the equation. In this case, you would put it on the right side because it's similar to a product that's being produced. But I recommend just keep it over here to the side. It just keeps things tidier. So after writing the balanced reaction, this is what we're looking for. So right there, that really is the main part of the answer. And to get this, you need to understand what delta H is. Now, last lesson, I mentioned there's a difference between Q and delta H. Q is just the heat. That's it. It's not really relative. It's not the amount of heat per something. It's just this much heat was made. Delta H is a more specific value. It's the amount of heat per mole of something. It could be per mole of a particular chemical, or it could be per mole. What sometimes people write is they'll write per mole reaction, meaning it's the amount of heat according to the balanced reaction, which could be a 1 mole for a chemical or more than 1 mole. And I'll talk about this unit again in a moment. So in order to find delta H, you must have heat, and it must be relative to something. In this case, it's going to be relative to this reaction, or the methane, since that was kind of our focus. So like usual, I have grams of methane, turn it to moles. So now I need to take the heat. The heat was given as 55.45. It's negative because it said produced, so that's what I have here. Divide by the moles, and that gives me the delta H. Again, I put the dot right there just to show 3 sig figs. And then I wrote it up here as my answer right there. Now, regarding units again, if you write this over here, kilojoules, that makes sense because it's per mole of CH4. This here, that's the moles of CH4. And so we could say kilojoules per mole of CH4, like I have here. And that makes sense because our balanced reaction just so happens to have a 1 right here. Now, if the CH4 didn't have a 1 in front of it, for example, if the CH4 had a 2, what that would mean is that we can't write this value according to this reaction. We would have to adjust it. So if it was negative 890 kilojoules per mole of CH4, if we want to write this alongside the reaction, you'd have to think, oh, okay, well, I've got 2 moles of CH4 according to the reaction, so I just double this. And so you could double this and then write it according to the reaction. In other words, it would be double that for 2 moles of CH4. But in this case, we don't need to worry about it because our CH4 was a 1. Another way to write the answer would be like I have here, kilojoules per mole of CH4. But if you can apply it to the entire reaction, it's better. Or, like I mentioned before, you can do kilojoules per mole reaction. And that's how lately the AP exam is really like this. And I believe what they're doing is they're just trying to emphasize that this energy value is not relative to one chemical at this point. We found it by comparing it to the CH4, but now that we know what it is, you can apply it to the entire reaction. So as I read this, it means there's going to be 890 kilojoules of heat produced for every 1 CH4 and every 2 O2 and every 1 CO2 that's produced and every 2 H2O that's produced. So you can think of the energy as part of the recipe now, in this case. All right. One way to find the delta H of a reaction, or a bond energy, if you know the delta H, is to look at what are called individual bond energies. I need a smaller pen here. So this means individual bonds, or as it says here, bond enthalpies. In this case, we're going to look at every covalent bond in the molecule. And we're going to use a chart, and the chart is assuming that we're looking at a mole, because of course one single bond between 2 atoms is almost insignificant. So we're going to look at a pile of them, a whole mole. And let's take a look at this table. So in our book, it's on page 211, but I have it here, right there. The top part, these are all single bonds, and you do it like a multiplication table. So for example, if you needed to find a carbon-nitrogen single bond, you would just find carbon on the left, nitrogen at the top, and you would say that that's 293. And notice that about half of the chart's empty because those would be repetitive values. Some interesting things to note would be, notice that it's kilojoules per mole. So this entire unit, always be careful when you read a chart. Is it joules per mole? Is it kilojoules per mole? Is it calories, kilocalories, or some other unit? Typically, we do things in kilojoules because it's a significant amount of energy and the usual way to do it. In the bottom of the chart, they have multiple bonds. And it's interesting to note, let's do nitrogen. If you look up a nitrogen-nitrogen single bond, you'll see its value is 159 on the top part. If you look up a nitrogen-nitrogen double bond in the bottom section, you'll see it's 418. And then a nitrogen-nitrogen triple bond at the very bottom right is 941. And what that's showing is that this is the amount of energy that it would take for us to break that bond. We'd have to put this energy in to break it. Or likewise, this is the amount of energy that would come out as you form the bond. And an interesting thing about nitrogen is a lot of explosives have nitrogen in them. So it's commonly known that fertilizers can be used to make explosives, and fertilizers are rich in nitrogen because that's needed by the plants. But in the fertilizer molecules and other substances, the nitrogen is not in triple bonds yet. It's usually going to be in single bonds. But as the reaction occurs, it allows, in the case of an explosive, it allows the nitrogen to become in its triple bond form. And this shows why it produces so much energy. It's because nitrogen really likes to make that triple bond. All right, back to the notes. What you do is you break all of your reactants, and this is always going to be endo because you're breaking bonds, so you have to put energy in to do it. And think of it this way, you're just taking the molecules apart. And then you also have to make your products. So as you make the products, you're allowing the bonds to form. You get energy back, so that's exo. And again, notice endo is always positive, exo is always negative. And then you just add up all your values. This makes it look more complicated than it is. A simpler way to look at it, break all your reactants apart, form all your products, add up all your values. So if we take a look at this reaction, here, into NH2 reactant to form NH3. We've talked about this reaction before. It's called the Haber-Bosch process, and it's a reaction you should just know. Again, yes, it does do equilibrium, but that is not our concern right now. So if you're thinking, hey, that should be a double arrow, we're not dealing with that situation right now. So to see or estimate, and notice it says estimate, this procedure we're using is not as good as some others, so it just gives us a rough idea what the delta H is. So that terminology is done like that on purpose. I have to break all of the bonds here and here, and then I have to form all these bonds. So yes, you're going to have to draw Lewis structures, so I've done that. Here's N2, here's H2, and NH3. And then from the chart, I've written down what the amount of energy is. So I've got a 941 for a nitrogen-nitrogen triple, a 436 for a hydrogen-hydrogen single, and I put the 3. You have to factor in the stoichiometry. And then a nitrogen-hydrogen is a 389. There's 2 of these molecules, but you have to be careful. Each of these molecules has 3 of these things. It has 3 nitrogen-hydrogen single bonds, and there are 2 molecules. So 2 times 3 is where I get that 6 from. And notice everything on the reactant side is positive, everything on the product side is negative. I've added up all my reactants here, all of my products here. You add it together, and you end up getting negative 85 kilojoules based on the reaction as written, or again, you could say kilojoules per mole reaction if you prefer. And we already discussed that earlier above. Things to notice. Obviously, if you draw the wrong Lewis structure, you're going to have problems. I usually don't get too creative with Lewis structures. That's not the point. So we're not really going to worry about deficient octets and expanded octets and all that weird stuff. We'll stick to the typical stuff here. Something to be aware of. This is the one time you don't do final minus initial. So normally, whenever you do a delta problem, you would do the final value minus the initial value. You don't do that here. This is the one and only time that I can think of at the moment where you don't do final minus initial. Just put in the energy to break your reactants apart, and you get that energy back as you form the products. If you do final minus initial, in other words, products minus reactants, you'll get the right value, but your sign will be the opposite of what it should be. I made a note here that the fact that nitrogen has such a high bond energy, this 941, it actually suggests that the reaction would like to go backwards from how it's written. And that is the case. We'll see that later on when we do look at the equilibrium of this reaction. It prefers the reverse of how I've drawn it here. And that will lead to some equilibrium discussions. All right, this next one, the textbook doesn't have any practice of this concept. So I make this part of our homework for this assignment. So if you want, you can just wait until you get to doing the homework, or if you want, just stop the video right now and try this problem for practice. And you see I've got it all worked out right here. Something to be aware of, we're not really covering this yet, but this is called an addition reaction. And in this case, C2H4 looks like this, C2, and then when you put your 4 hydrogens like this, you'll realize, oh, my carbons don't have an octet, so then you think, oh, I'll just pop a double bond in there and that fixes it. And you can do it the method where you go through the Lewis structure and counting valence electrons, or you can just figure it out like this. What happens in this reaction, just to give you an idea what's happening here, is you can think of the double bond as getting rid of the extra one, and half of it goes here and half of it goes here, and that's where the chlorines attach. Of course, that's not exactly how the atoms accomplish this, but it's an easy way to think of this. And again, it's called an addition reaction because you're adding these to the molecule. You're not removing anything. And this is just a very basic organic chemistry reaction, but we don't need to get too much into that because that's not this class. All right, last thing here is something called a bomb calorimeter. And of course, people think when they see bomb, they think that it's going to explode, and that's not the case. Bomb basically means to do something quickly. So if you think about an actual explosive, it blows things up because it reacts very quickly. For example, if you take a big rock, apparently my rock looks like an apple, and you put a stick of dynamite in it, like so. We've got our fuse. And you light that dynamite. The reason it blows the rock apart is 2 things. It produces a lot of gas and heat, but it does it very quickly. If you imagine the dynamite doing its same exact reaction, but very slowly, if that was the case, the gas would just slowly fizzle out of the opening and it wouldn't cause any damage. The trick to making this work is to do it quickly. And that is similar to what this machine is doing. So this is an actual piece of equipment And the word bomb means to do the reaction quickly. The reason you need to do it quickly is because heat is a pain to deal with and measure. Heat is constantly moving. It's either coming into your system from the environment or leaving your system to the environment. So if you want to do a good job and get a good measurement, you need to do it quickly. So this piece of equipment here is designed to do a reaction fast, measure the heat that is either produced or consumed quickly before it has time to interact with the environment very much. Calorimeter, calorie, just think heat, meter, measure. So you can think of it saying, read it backwards, measure heat quickly. I mentioned two versions of the Q equation. Our normal version, Q equals MC delta T here, that's what we'll normally deal with, but I do need you to be aware of this version. You can think of this top one as Q equals meat, and the second one is Q equals cat. Actually, it looks more like cat than the other one looks like meat. This big C is known as heat capacity, and that you can think of as a combo of the mass and the specific heat. And this would be specific to a particular machine. So this particular bomb calorimeter down here at the bottom, it might be given a value in which if you are using it for an experiment, it might say it has a heat capacity of a certain value, and that would be relative to that exact machine. And of course, assuming you're using it correctly. Let's take a look at the actual machine. There's a better picture in the book. I think I referenced it. Yeah, it's here. So feel free to look at the book, page 200. I don't have it available. It's just better quality and color and such. We'll just look at this one. So the way it works is you put your specimen. So let's just do something obvious. Let's say we're going to burn something quickly. So let's just say we have a little container of like a piece of paper or something in here. And you would put it in here in the middle. And we want to determine the heat that comes out as this little piece of paper burns. Or if we wanted to get more detailed, the enthalpy or delta H. So you put this in the middle, you surround your sample with water. The reason you want to surround it so water would be in all dimensions surrounding it. It would even be in the front here as well, where we just wouldn't be able to look through. And water makes a great substance to contain the heat because it has such a high specific heat. It's good at holding heat and not letting it go. A few more things here. You'd have a motor and this little thing spinning here to switch colors. This thing would be spinning here to stir it up. You would probably have some sort of system for detonating. So in this case, it's assuming that we're going to detonate something. Again, I have my little piece of paper here, and that would be hooked up to some system that allows you to actually detonate it. And you'd have a thermometer of some kind to measure the temperature change of the water. So what you do is you don't actually measure the temperature change of the reaction directly. You let the reaction happen. In this case, it'd be exothermic and it would make heat. The heat would go into the surrounding water jacket. And in the water, you measure the temperature change. And you'd have to be careful with your results because in this case, the water would absorb energy. So as far as the water is concerned, it would be endothermic and its temperature would go up. But ultimately, it's not the water that we care about. It's the reaction that's taking place within the water jacket. So if heat went into the water, that means heat came out of the reaction. So as far as the reaction's concerned, it would be exothermic. And so you'd have to be careful and make sure that you reference this once you start talking about the reaction that's happening, because it's not the water that we really care about. The water is an indirect way of figuring out how much heat was involved. Let's see if there's anything else in here. No, that really covers it. I didn't put an example using this equation, but there is one in the homework. And when you go to do the homework, you might first think that you're missing something if you try to use Q equals MC delta T. Instead, use this and it will work out for you. And that takes care of this section of notes.